So this is actually my very first summer school. I've never been to one before, and I don't think I've given a lecture since I've been at DeepMind, so you may have to bear with me. Um, but yeah, I do want to actually ask, just to get started, maybe by show of hands, how many of you know anything about like multi-agent systems or multi-agent learning? Okay, so a pretty good number. So I will say that in this talk, I really try to. There's a disclaimer. There's no like results. So this is really going to be focusing more on intuition, and I think of it more like a lecture, like an intro lecture, where we're trying to focus on how people use multi-agent systems in the age of foundation models. So how people are kind of broadly using them in the field, where there might be some challenges and exciting opportunities, and hopefully, I want you all to come away with a strong intuition. So first, we're going to talk about motivating the use of multi-agent systems, and then defining multi-agent reinforcement formalisms that are relevant to the kinds of systems that we're thinking about, reasoning through multi-agent systems, learning and adaptation with multi-agent systems, and then some concluding remarks. So this is a quote about AGI, which probably many of you know. Google DeepMind has been pursuing AGI for many, many years, and it's something that we're still excited about and as an organization still have a mission towards. So this quote says, "Artificial general intelligence is an important and sometimes controversial concept in computing research, used to describe an AI system that is at least as capable as a human at most tasks." So this is kind of the base of what we're thinking about is AGI agents. And in particular, we're thinking about AGI agents that are interacting and assisting humans now in the age of like chatbots. So here are two different axes to just kind of help us describe the problem space. So one is around the complexity of user-based interactions, so single-turn versus multi-turn interactions. And the other is around the complexity of the reasoning problem for the agent on the back end. And so like single-step reasoning versus multi-step reasoning. So at the very the simplest problem is response generation, but this is not necessarily a solved problem because it has lots of challenges still that go along with that. And then here, when we think about like multi-step reasoning, so a single-turn interaction, but multi-step reasoning. So for example, an agent having to prove a theorem, or like working through many of the math or reasoning problems might be single turn with the user, but the agent has to step through many different steps. You can think of like chain of thought, many different steps of reasoning in order to get to an outcome or solution. And then a multi-turn interaction that might be single-step reasoning is something where the reasoning problem itself for the agent may not be difficult, but there may be back and forth with the user. So like some kind of dialogue or active learning could also be this kind. And then in the hardest kind of section are like games and complex problem-solving kind of dialogues where there's continuous back and forth. There's also multi-step reasoning required by the agent. So when we're thinking about people using multi-agent systems, we're thinking about this entire space. People can use multi-agent systems for any of these kinds of problems in order to, produce better outcomes or better tasks or better solutions for AI agents. But oftentimes they're more well-motivated in the more complex part of the space. So with that being said, so a lot of these problems are really complex and difficult to solve, but there's been a huge opportunity in the field with the scaling laws of neural models. So basically what I want you to see in this image, so this on the x-axis you have a logarithmic scale, and on the y-axis what you have is some measure of loss. And so this particular paper highlighted that in many different domains with many different types of modality, as you increase the compute on a logarithmic scale, then the loss goes down accordingly. So it gave us a lot of reason to be excited that like scaling up compute in and of itself is a key aspect of like solving some of the hardest problems that we want to solve. So then this is another paper that looked at neural scaling laws with respect to data. So in general, like compute, models, data, the optimization algorithm can play a role, but like looking at like how does the loss go down as a function of when we scale? And so here, this communicates that a similar finding that as we scale the data exponentially, then the loss has a corresponding trend of going down. So it suggests that there's an opportunity in taking advantage of scaling both compute and data in order to improve the kind of hard problems that we want to solve, even in a single agent paradigm. However, there are some also persistent challenges. For example, hallucinations are still a persistent challenge with AI models, and in fact, they're getting more sophisticated, so they're more difficult to detect. And then there are some other real challenges when we think about the paradigm of one single all-powerful model. So, for example, starting with robustness, if you only have one single AGI, then you have one single point of failure. So, and the more you the more you scale, the more you have complexity in the model, and you have one single point of failure. So this can be much less robust, right? And increasingly, so again, there's increasingly convincing hallucinations. So the idea there would be that if you had a multi-agent system, you have more redundancy in the system, which adds robustness. You have, if one agent is failing, you have other agents that might be able to take up what the agent is doing. You can also more easily detect hallucinations or errors if other agents are trying to solve some of the similar problems or trying to solve parts of the problem. So loss of plasticity is also an important problem. So the continual learning problem is the problem of as the agent is increasing its, as it sees more and more data, it gets to a point to where the model is not able to learn as much anymore. So it's not as plastic. I mean, this also happens with human brains as humans grow. And so again, now if you can distribute the compute, then you start to maybe circumvent some of these challenges with loss of plasticity. And then there's this idea that autoregressive models, since it's token by token generation or autoregressive token generation, right? So then the next token is conditioned upon all previous tokens. Then it's really geared towards system one thinking, which is fast thinking and small decisions. And we want improved system two thinking, slow thinking, complex decisions, reasoning. And so the hypothesis here might be the interactions between agents might be able to aid in the reasoning process. Other real challenges, so evaluation and optimization challenges. So, with some types of domains, there's often no ground truth. So you really want a best response. For example, instruction following. There may be many different ways to follow instructions correctly. So let's say an example would be, I want an agent to tell me what's a good movie theater, based upon my interest, right? There are many different correct or high quality solutions to that. But if you think about the space of English sentences, there are many more that are incorrect or that are not very good. But not having a clear ground truth means that we're reliant on auto evaluation methods like reward models, et cetera. And this is still also an open challenge. Evaluation is multi-objective. We want to trade off many things. The objective function is not directly observable and is task dependent and largely subjective. So, and then also data challenges. We oftentimes have poor data quality, and a lot of our advances have been based upon supervised learning, right? Like supervised fine tuning and pre-training. And then insufficient coverage of certain domains. There are some domains where we don't have as much. For example, you wouldn't expect that we have a lot of data on, I'm blanking, but maybe something like, differential geometry as compared to algebra 1. So potential benefits of a multi-agent system, given that we are thinking about cooperative goals and value-aligned systems, agents can have synergies, so different capabilities, knowledge, or skills that can synergize. Division of labor and parallelization of the workload, so you no longer have the single point of failure. Data diversity, particularly if you have agents having different specializations, so potentially higher coverage of task space or solution space, or both. Evaluation robustness, because now you can have multiple agents, like a mixture of experts that are weighing in on the evaluation problem. So several judges or reward models. And then also agents can inherently represent different objectives. So these are some of the promises of using a multi-agent system. So maybe let me pause for a second there. Are there any questions? All right. Great. And then this is just basically saying, cooperation in society has allowed us to achieve some really huge feats that would have been difficult or impossible to do on our own. And then this is an example from biology. I actually really like these a lot. This is from thinking about complex systems where you have like a huge population of very simple organisms that are decentralized. And then, so here what you see is an ant colony. They need to cross a bridge to get over, and they emerge this behavior of like forming the bridge, and then other ants like walk over, and then the bridge gracefully degrades. And this is like an image depicting like immune cells in the human body that are also decentralized. And they, when there's like let's say a cancerous cell, they like in a decentralized way, they come together and like attack the invader. So there's some really cool collective agency in biology that we can take inspiration from. Okay, so defining multi-agent reinforcement learning formalisms. So again, this problem of the generally intelligent agents that are able to maximally be helpful to humans. So we want to go from a single generalist agent to general purpose multi-agent system, like a society of minds. This is kind of what this picture is showing. And so over here you have these agents that are basically in like groups or coalitions that are, presumably working together in some cohesive and cooperative way. And then this is kind of two different paradigms for thinking about how we might use multiple minds. On the left, this is supposed to depict multiple agents working on the same problem. So this is like n different agents, and what you might want is just the best of n, like all of us work on it and see who gets the best answer, which is a very different usage than the picture I just showed, where we're, maybe taking on specialized roles and like cooperating. So maybe there's more of like a divide and conquer here. All right. So fully cooperative multi-agent systems. So in your intro to RL, I'm assuming that you learned about Markov decision processes. And so when we talk about fully cooperative multi-agent systems, these are formalized as decentralized, partially observable Markov decision processes. So here you have a bunch of different agents. And so all of the agents will individually get observations from the environment. That's the partial observability, is that they can only see their observations, not the true state. All of the agents are able to take action in the environment, just like any other Markov decision process, but you have several of them happening in parallel. And the world, the environment, provides a transition model and a reward function, just like it does with a single agent MDP, or single agent POMDP. But here in particular, you have the transition function takes into account the true state and actions of every single one of the players, and then tries to make a prediction on next state based upon that. So actions of every single player we call the joint action. So it takes the state and the joint action, which means that there's an exponential increase in the transition function and transition dynamics, because you need a cross product of all of the different actions that all the agents can take. And then the reward function for the fully cooperative setting, there's only one reward for the entire team. So a key challenge in multi-agent reinforcement learning in general is that the environment is non-stationary. So because the environment is what provides the transition function and the reward model, in a single agent formalism, as a agent, if I'm in a particular state and I take a particular action, then I expect that the distribution over next states or the distribution of rewards should stay stationary throughout the time that I'm learning. So even though I may not know what the distribution over next states is or the distribution of rewards is, I can learn that over the course of the reinforcement learning process. In a multi-agent system, if I'm in a particular state and I take an action, the same action later might give me a completely different reward or completely different distribution over next states, because the next state that you land upon, the reward you get is dependent upon the actions that all the other players took. So even if I'm in the state, and let's say the state is that I'm in the kitchen, and my action is that I'm pouring milk, and then maybe I hadn't thought this example through, but maybe you could imagine that maybe one time, if I'm a single agent, then I don't have to worry about anything else affecting me besides the environment. And so maybe I learned how to pour, and then with some probability I end up in a state where I have a full glass of milk. But in the multi-agent system, let's say some of the other agents are like, little kid agents, and then you take the same action, and then with some probability the milk is splashed out of the floor and the glass is broken, and you're thinking, I took the same exact action, why did this change? And it's because the other agents are learning at the same time as you. And if your little kid was learning how to really wreak havoc at the same time you were learning how to pour milk, then you can imagine how it lands you in a very different state. And it's not because of your actions, because of the actions of other agents. And that's also true for the reward, because you can imagine that those are going to yield very different rewards. So it's non-stationary from the perspective of any agent, because other agents are also learning at the same time, and the dynamics are changing very, very rapidly, particularly in the beginning of training. And then this is the mixed motivation setting. So the setting I just talked about was fully cooperative setting, where every agent has aligned incentives. We're all on a team. We just want to coordinate or communicate effectively in order to get the team reward. And in this setting, one problem that's actually a very key challenge is what we call the multi-agent credit assignment problem. So if I'm on a team, even though we all have the same incentives, we're all on a soccer team, football team, and somehow we don't get the point, or we don't do very well, right? I don't know you don't know which of the agents caused that particular outcome. So you can't assign credit to which of the agents, because all the agents get the same reward. It's just one team reward. So it's not clear if my actions actually messed us up or my actions actually helped us. So this is actually a really key challenge. But here, this problem of in the fully cooperative setting, we all want the same thing. It's just a matter of how do we coordinate and communicate effectively to get it. So maybe I need to explore and kick the soccer ball better next time, or something. Or, sorry, the football. Whereas in a mixed motivation setting, so this is a classic, one of the classic settings for mixed motivation, but you have a cooperative goal is social dilemmas, where you want people to cooperate, kind of the tragedy of the commons. You want people to cooperate, but people have different incentives, or climate change. You may want people to cooperate, but people have different incentives with respect to this. And so that means that in this, and how that changes the formalism, the key thing is that the reward, every agent gets their own reward now. So now a key aspect of cooperation when you're in this mixed motivation setting is getting agents to align their incentives. And this is important for LLMs, because you're going to have agents that are going to be adversarial. You're going to have safety concerns. You're going to have agents who actually just don't care about your interests. Maybe they're not trying to be your adversary, but they just have different incentives than you do. And so it's important to understand that even if you want agents to do something cooperative in terms of the outcome, if agents have different incentive structures, you have to figure out how to get those incentives aligned towards the cooperative outcome. Okay, and then in LLM domains, observations or state comes from a context. Actions are the responses that the agents can take. Transition dynamics are some probability of the next state of the conversation given the current context and the agent's response, which is the action. And the reward model is based upon the outcome of the entire interaction, which you can consider a game. All right, so now, given that, that's mainly just giving you the formalism foundation, but I'm actually not really going to return to it that much. Now we're going to go through some of the different ways that people configure multi-agent systems as an improvement operator to aid in reasoning. So in this diagram, you have a task, which is typically a form of a prompt, and context, which you can consider your state, and which is coming from the environment, and then you have some agents in the middle. So some system of agents, you can think about them like a system on the back end, and they are producing some solution, right? And so in general, when we talk about a multi-agent system used for reasoning as an improvement operator, then what we want is improved reasoning through having these multiple minds. So the multiple minds, again, can provide robustness or diversity. So one of the things I talked about earlier is that some of the key challenges with data is that, and we saw from scaling laws, having more data, but it has to be high quality data, can really be powerful for enabling models to learn and to take down the loss. But the data needs to be quality data. It can't be poor quality data, so it needs to be high quality data. And it also needs to cover the space, meaning it needs to effectively be represent the same underlying distribution as the data in the real domain. Like the data that the agent sees needs to represent the same distribution that the data in the real domain it operates has. So having diversity of data to get more coverage of, the kinds of responses or solutions that are correct is actually a really important part of helping the models to improve their performance. All right, so the goal here is to improve the solution. And so this is a multi-agent system as an improvement operator. But another way we can use a multi-agent system is, again, as a society of minds. If you remember that picture earlier, and I had one of them was, multiple minds which were operating independently, and another is there's actually interaction, coordination, cooperation, some kind of collective intelligence that we want to take advantage of. So again, the goal is to improve the solution. But here, a key thing here is that I added these arrows. Probably should have highlighted them. But if you see it in the top picture here, there's just like dots, meaning that they don't have to have any interaction. And then this assumes that their agents are interacting. And so not edges, they're edges, like edges of a graph, right? If agents are nodes. So some edges can be thicker, meaning maybe they're more important edges. Some edges can be bidirectional, like interaction can flow in both directions. A dotted edge versus a solid line edge might mean two different types of things. They may be two different types of interaction. So you can have rich graph structures when you have interactions between agents in order to try to produce this kind of collective intelligence effect. Okay, so zooming out a bit, on the left side, you're for any reasoning system that you're using to try to solve a task, you are going to have a task prompt and some context, right? And that's going to go as input to the reasoning system, and then the reasoning system is going to do whatever it does in order to think, right? So whatever that method does, and then it produces some solution at the end. And so the idea here is, I meant to put a greater than symbol, but the idea here is you want this solution to be better in some way than that solution. Yeah, so when you're comparing, so the idea would be that if you're going to be using a multi-agent system, and one of the things I haven't really talked about is the fact that this is multiple LLMs, which is quite expensive, right? So if you're going to be using something that is potentially more resource intensive, even if your multi-agent system are smaller LLMs, like let's say here I have Gemma, 1B models, and over here I have a Gemma 4B or Gemma 27B. Okay, so maybe it's not, but the point here is that you do have to think about some trade-off between compute and like actual performance. Like, what do you get from that, right? And presumably, if you're using a multi-agent system, then you have some performance metrics like benchmark accuracy, practicality, or robustness, like pass at K. Pass at K is, if you say pass at 1 means if I sample that method only once, what is the percentage of the time that the method passes, that it gets the correct. But pass at 10 would be I can sample 10 times, or pass 100 means I can sample 100 times and you take the max. So the higher the K is, the more chances a model gets in order to get the maximal output. But it's not very practical to have models that only do well at pass at 100, right? You want it to be pass at a smaller K. So these are some of the things that resource usage. So you want to be able to compare models along these axes. All right, so let's look at some instantiations of how the literature has used multi-agent systems for improved reasoning. So here, and these are all going to be diagrammatic, so they're quite intuitive. So here you have a bunch of agents. This is going to be the simplest paradigm, and they all What's not set, what's implied here, but I didn't actually put, is that each of these agents is outputting a response. So every agent is taking an action. And then there's going to be some selection or voting mechanism, and then there's some best or voted solution based upon that. So best of N is kind of the simplest configuration, but I'm pretty sure it's still one of the best performing methods out there. And it's literally just in different samples, and then you take the best one that's based upon some auto-evaluator or reward model. So it's just simple selection, but it's really powerful. And then you have some of these other some other works that have looked at other like voting mechanisms in order to try to see if we can get a better solution there. One of the things that is implicit here, so you know, I've done work with pretty much all these paradigms myself, and in my internal work in DeepMind. And one of the things that's really key about the multi-agent system and why it's so powerful is the diversity of responses. You get much more coverage of the space, and then you might be able to find local optima that are better than the local optima that you've already been moving towards. All right, so hierarchical decomposition, so divide and conquer. So this is, So here you see that I have decentralized structure, so there's no centralization, and there's independent generation, so they're independently generating in parallel. So here in hierarchical decomposition, which is a divide and conquer kind of mechanism, you have some kind of manager or controller, and then that agent is delineating something like maybe task allocation or role assignment to different other agents, and then as a collective, there's some solution that they arrive on. And so presumably here, you need to have an aggregation operator or some kind of iteration operator, which I don't say here, but in order to like decide what that, or maybe the manager or controller decides what that is. But this is kind of the general structure, and it's centralized because you have one agent that is able to delineate tasks. All right, so cooperative debate, refinement through divergence. So here you have, so there are some different ways to do this, this kind of cooperative debate. The one that I'm honing in on is the one at the top, reasoning through factuality and reasoning through multi-agent debate. And that's one of the highly cited ones, multi-agent debate paper. So decentralized structure, peer-to-peer observations or discussion. So in this paradigm, you have an agent. That agent comes up with some solution, and then it can observe its peers' solutions. And then, actually, in this top paper, they don't actually do any interaction, but in these other papers, there's some interaction between the agents that takes place. And then, so in the top one, the reasoning through multi-agent debate, that agent will infer some changes based upon what it observes from its other peers, and then it goes back to observing again. And this is actually happening for each agent. So if there are K different agents, each of the K agents will generate a solution, have the opportunity to observe all the other agent solutions. It's kind of like if you guys are each of you doing a homework assignment, but now you can observe everybody else's, and then you can like update yours and change it, and then, do this over T rounds before coming up with the best or the consensus solution. Although it's called debate, but it really is more like a consensus. So here's some analysis from a couple of years ago when I was doing some experiments with this method. So first, as a baseline, here's a critique revision. Oh, can you read that? Okay. So the human, the prompt says, if I take half a glass of iced tea and pour in half a glass of lemonade, what will I have? And the initial response from the agent, so this is not multi-agent debate yet, but I'm giving this as a baseline to compare against. And then the agent says a half and half of iced tea and lemonade. And then the critic says, system's last response is helpful because it provides a concise and accurate answer to the human's question. The response is also free of any harmful content. And I don't exactly remember what my instructions were, but presumably it was something about helpfulness and harmfulness. And these methods were very, and still are quite sensitive to prompting. So there's a lot of prompt engineering. And so then the agent's revised response is, if you take a half of a glass of iced tea and pour in a half glass of lemonade, you will have a half and half iced tea and lemonade. So basically nothing changed. So this is like a juxtaposition to say, okay, so you have a critic, and let's say the critic can't find anything wrong. The critic also doesn't have anything to compare against, neither does the agent. So by comparison, the multi-agent debate method, same prompt, what will I have if I pour half iced tea and half a glass of lemonade? And then initial response, and around, by the way, in the US it's called an Arnold Palmer, so I don't know if you have that context. Definitely not half lemonade, half iced tea. And so then, so the assistant says, one assistant says you will have a glass of Arnold Palmer. And another assistant says you will have a glass of half iced tea and half lemonade. And so, mind you, if this were best of n, it would be like best of 2, and you just stop here, and then a reward model will tell you which one is the best one, and it get returned. All right, so now both assistants have the opportunity to observe each other and see what they said to the same task. So now, round two, assistant one, who first said you'll have an Arnold Palmer, says you'll have a glass of Arnold Palmer, which is a mixture of half iced tea and half lemonade. And then the assistant two says you'll have a glass of Arnold Palmer, which is a mixture of, okay, so they basically say exactly the same thing. And then in round three, so they can observe each other yet again. And then assistant one adds something to it. You'll have a glass of Arnold Palmer, which is a mixture of half iced tea and half lemonade. Additionally, you will have created a refreshing and delicious drink that is perfect for a hot summer day. Okay, I don't know where I got that from. But, and then assistant two says you'll have a refreshing glass of Arnold Palmer, a summertime favorite that is perfect for any occasion. So they actually both changed. But I think this is, really trying to illustrate the fact that this having some kind of comparison or juxtaposition is really helpful or impactful for enabling agents to figure out another solution. You can think about it like if you have the opportunity, if you're working on something solo, you only have your own priors. But if you have the opportunity to even just observe other people's solutions, you might see some creative solutions to the problems and it gives you some new ideas. And so this is, it's powerful, Justin, but a key part of the power of this is that the agents have to have different responses, otherwise different solutions. If they all have the same thing, then it's actually not helpful, right? So there has to be diversity so that agents can take advantage of that. All right, I'm gonna skip that science example just for the sake of time. So adversarial negotiation. So the last one was called cooperative debate. So it's really about like discussion in a way that is still cooperative. And this is around optimal decisions through competition. So now you just have a bunch of agents that are peers. They engage in some kind of negotiation and each agent can like score each other. This happens for T rounds. And then there's a negotiated solution. So, I mean, in structure, it looks very similar to the last one, but the key thing here is that the agents there's more of an air of dissent from the other agents, and agents need to try to negotiate their own positions. And the agents also can score each other here, so it really does take on more of a negotiation type of flavor. Yeah, and then this one is interesting. Gemini suggested to me, but I think it's quite interesting. It's a very different kind of paper. So it is a decentralized structure, but the key thing, the simulacra is really around agents just like living their normal lives and everyday activities, and it's trying to produce believable individual and social behaviors and emergent social behaviors. So this is a different kind of flavor, but I thought it was interesting to show that like you can also have these kind of configurations to produce different types of outcomes or different types of policies rather. So this is my intuition for why these kind of methods are helpful in terms of improving solutions. So this is an abstract optimization landscape, which is peaky. So this is supposed to represent something like instruction following or creativity, where each of these peaks could be a high quality solution. And presumably this space will go out into infinity, and a lot of the space will be very flat or very low valleys. But so one agent's response is going to presumably fall on one of these peaks. So an agent, comes up with one reasonable solution. Maybe it's not the top of the peak. And then if there's some kind of source of correction, then this allows the agent to make some kind of small delta towards a better solution. So for example, a critique, response kinds of paradigms could help this to happen. Okay, so now, but when you have multiple agents, from my perspective, the value here, again, this diversity, is that agents, what you really want them to do is sample different peaks. You really want to get them to like explore more of the space, because it could be that the peak that you would be converging on is actually not the correct peak or not the highest peak. And so the value of multiple agents is more coverage or spread of the optimization landscape. And you can imagine if you had like a huge population, you might be able to get even more spread. And something like the multi-agent debate, what it did is when the agents were able to observe each other, they basically combined parts of their responses to a better response. So it's like if you're familiar with genetic algorithms, it's like the recombination operator, the crossover operator, where I take part of my response, I take part of your response, I put them together, and now I have something that presumably might be on a different peak, and it's actually even better. So it's really trying to enable exploration, like guided exploration through social interactions. And then if you had some other mechanism to provide correction on top of that, you can imagine that you might be able to get even better. So some interesting takeaway from this line of work. My observations when I investigated these types of frameworks, observation of different agent solutions, multi-agency led to better solutions, presumably because of the data diversity that it offered. Time to iterate on solutions seemed to help sometimes. So iterative solutions like, for example, so we didn't talk about this, but something like chain of thought would allow an agent to like continue iterating on its reasoning, or actually just giving agents longer time to think. These thinking models currently have longer time to think, and so that is oftentimes very helpful. And instruction prompts matter a lot. So there was a lot of prompt engineering that I experimented with earlier in that project, and I remember that making a big difference. But even in interacting with the language models today, the kind of the prompts actually matter quite a lot. And then with auto-evaluators and reward models, progress has been made, but this is still an open problem. So there's a lot of overfitting with respect to reward models. There's a lot of subjectivity, particularly when you're talking about humans evaluating. So this is critical, but it's critical for open-ended problem domains like instruction, following, creativity, et cetera. But it's still an open problem. And so these methods are also kind of sensitive to that. So now taking a step back, what factors make it such that the multi-agent system was only able to impact the solution being outputted? So typically in these setups, the agents themselves have been pre-trained and are static. So the agents are not, like, remember I showed you those multi-agent formalisms to begin with, but typically in these, the agents are not continuing to learn. It's oftentimes at some kind of inference time, compute. The task distribution is given and stationary, so the task that they're getting to solve, it's all about like improving upon the solution or the response, but the agents are not directly impacting the task, and the situated environment is stationary. So importantly, agents have no affordance to change the task distribution or the environment. But what if we had agents that were co-learning and co-adapting and have the capacity to directly affect the environment and the task distribution? And so this is really around learning adaptation with multi-agent systems. And so, before we were talking about multi-agent systems as an improvement operator, so I'm playing with this, but multi-agency to provide an evolution, like an evolution mechanism. And so in particular, what I mean by that is, here's what we had before. So this is the multi-agent system as an improvement operator. The task and context come in. There's some multi-agent system that's reasoning, and it produces hopefully a better solution than the single agent system would have. So now this multi-agent system as an evolution mechanism, it's not only the case that the system is providing a solution, it also has the ability to change the environment or change the task distribution fundamentally. So the goal is to evolve a task distribution that is more indicative of the kinds of challenges that the agents need to be solving. So this is my attempt at trying to give you a sense of what multi-agency and open-endedness look like. So let me talk through this. So here you have a bunch of different agents, and there's some environment that they exist in. And you might have coalitions of agents that actually form. So agents within a particular group might interact more or more cooperative. Agents across groups may interact less or are more competitive. So there can be complex interaction dynamics at play, and there are lots of different agents. But importantly, the agents are not only importantly here, the agents are learning over time. They're co-learning, so they're able to impact each other's policies, more like the paradigms that we talked about in the beginning, and they're able to adapt their environment. So, for example, let's say you had agents, let's say you had things like wood and metal, and you had some basic materials, but you didn't necessarily have, chairs and couches, et cetera. And you have agents that are in some environment. Do I talk about this? Okay. So you have agents that are in some environment, and you have some kind of pressure on the agent. So they need to be able to eat in order to thrive, or they need to, let's go with that. And they also need to be able to be safe. So in order to do that, the agents have some kind of environmental pressures. Now maybe the agents use the materials like the wood and the metal to create something like a house structure, or you can think about basic edible ingredients like to create food that didn't already exist in their environment. So they're actually directly impacting the environment itself and changing it, and then that changes what tasks they can do in that environment. So now that we've built a table, agents can set the table and eat. Now that you've built a house, agents are able to clean the house, right? So actually, the environment itself is open-ended, and it affords agents to change the environment, increase the complexity in the environment, and then that also changes the distribution over tasks that agents encounter. And so here, agents are learning in parallel. The environment is non-stationary because agents have the ability to directly impact and change the environment. Again, there's co-learning between agents and co-adaptation between agents and the environment. So agents are impacting their environment, but they're also changing according to their environment, like changing their policies up according to it. So it means both the environment and the task distribution can change over time. So as a nice example of this, I'm pulling up some work from the auto curricula literature, which is really around right at the intersection of multi-agency and open-endedness. And so this is from StarCraft, Alpha Star, which was in Nature in 2019. And the image itself is just, I think I'm just trying to give you the intuition that in this kind of environment, agents are able to directly build things, change things in the environment, make the distribution over tasks change as they are interacting with each other and with the world. And in particular, this derived from self-play and agent leagues in Alpha Star. So in self-play, agents are co-learning at the same time. And so as I learn, as my opponents learn how to better do certain things, I learn how to better do things to best them. So my environmental pressure is coming from competition largely. And so we're both learning, and then the challenges become harder and harder. But this is like this co-learning happening in parallel and co-adaptation of the environment. So this is from the hide and seek paper, OpenAI, and that was around the same time, a little bit later. And this is, I think these are images from like a demo, but there's like a cool things where on the top right one, this triangular structure is a ramp. So, the agents started with a very, very simple environment, and they started learning. The red and the blue team are playing hide and seek, and they started learning how to build really complex structures in order to best their opponent. So this is a ramp where the agents would like run and like jump over the ramp and hide under something, and or building like walls. And here the blue team has built walls to protect themselves from the red team, and now the red team's gonna have to find some way to get over the walls. And so agents come up with really increasingly complex and sophisticated strategies. They're learning to improve as their opponents are improving. They're getting better through the competition, but they're also adapting their environment, and there are new tasks for them and new challenges. And a lot of video games would have this, right? Where, not necessarily saying they use AI, but where the environment is being adapted and there's increasingly new challenges. So there's been more work on multi-agency and open-ended learning since then. But this is still very much an open question as to how to leverage this technology for iteratively leveling up of foundation models. So in particular, I brought that up to say that it's really exciting when we saw this work in these kind of game settings, but it's still very much an open question. And part of what's really cool there is that the tasks the task distribution is evolving over time. As the agents' policies are getting better because they are interacting with each other in ways that force them to improve, they are not only co-learning, but the environment is changing and the task distribution is changing. The challenges the agents have to solve is changing. So this is a really powerful paradigm for thinking about, can we use this to get us closer to push towards AGI with foundation models? Foundation models are very powerful, and currently our limitations have been really tied to like supervised learning and ROXF. But like there's a real power when we think about multi-agency and open-endedness together to really push us to new distribution over tasks that are meaningful for what the agents need to solve, that our data sets are not necessarily giving us, and also that agents interacting with the environment by themselves without some kind of selection pressures or competition pressure wouldn't encounter, which would be like the single agent RL. Okay, so that is, so just some concluding remarks. The key things I talked about here were multi-agent systems being increasingly employed as improvement operators. And so, and here, this is really about the reasoning problem, like using a multi-agent system to improve the reasoning. And oftentimes this is at inference time, but this is using more compute. And but many design choices impact how effective they are. So like the number of agents used, the specializations or the roles, ability to increase the solution coverage in a meaningful way. So like, again, that diversity aspect is really key, because if you don't have diversity, then you might as well just have one agent. You don't need to have more compute unless it's actually giving you something valuable. But it can't just be diversity for the sake of diversity. If you think about peaks, right, it has to be a peak that is at least as high as the peak that you have, or even higher, so you're discovering something new that's even more valuable. And so how do we unlock multi-agent systems for even more improvement as improvement operators? But then there's this whole wide open space of multi-agent systems situated in open-ended environments as evolution mechanisms or adaptation operators. Again, I'm playing with these. And really looking at how do we explore this learning paradigm with foundation models in order to repeat some of the successes that we saw with these complex games, and evolve our task distribution so that we get closer to not only like solving artificial general intelligence, but moving beyond artificial general intelligence to artificial superintelligence. So ASI is definitely going to require data that's simulated, because it by definition, artificial superintelligence means that it's outperforming humans, right? And so RL and multi-agent and open-ended learning have a key role to play when we talk about going beyond what humans can do currently. And so this bottom area is really exciting, because it's really like trying to take advantage of some of the learning paradigms that we've had in classical multi-agent RL spaces or RL spaces, and with open-endedness, and then combine that to like unlock new task distributions, new challenges that are going to be relevant to agents solving challenges that we haven't been able to solve yet, but that we also don't have the data to give them to solve. And maybe humans are not as proficient at it, but agents could, by self-play or training through leagues or et cetera, learn how to gain even more proficiency than humans. Yeah, and I think that's it.